Так, ну давайте начинать. Рад представить нашего последнего для этой школы лектора, четвертого нашего лектора Дмитрия Петровича Ветрова, профессора Высшей школы экономики. И Дмитрий обещал нам рассказать про введение в диффузионные модели. Мы сегодня уже чуть-чуть слушали от Евгения Бурнаева разные истории. И теперь как раз настало время понять все-таки, что такое вот эти диффузионные модели. Спасибо.
Алексей, спасибо. Добрый день, уважаемые коллеги. Действительно, я хочу поделиться немножко своей интуицией и свои скромные знания в области диффузионного моделирования сегодня рассказать. Основная мотивация какая? Я думаю, многие, если не все из вас знают, что диффузионные модели сейчас — это что-то типа такого парадигмального сдвига, то есть они производят революцию в области генеративного моделирования, но по меньшей мере такую же, которую в дискриминативных моделях произвели трансформеры, а может быть даже и больше. То есть они выбивают соту на всевозможных задачах генеративного моделирования в разных доменах и плюс обладают некоторыми очень интересными свойствами с прикладной точки зрения, которые позволяют кучу разных модификаций делать над диффузионной моделью. В первую очередь я говорю про задачи так называемого условного генеративного моделирования, которые, как правило, представляют гораздо больше практический интерес, чем безусловное генеративное моделирование. И дальше мы... еще одно вводное замечание. Вот почему лично мне нравятся диффузионные модели, потому что в них, в отличие от многих современных техник глубинного обучения, снова появляется красивая, элегантная, местами непростая математика. Что мне, как человеку с математическим образованием, очень приятно. Потому что последние годы какой-то дрейф был, что математики все меньше, эвристик все больше, понастакаем там больше слоев, каких-нибудь self-attention добавим, нормализацию добавим, и вот профит. Ну, с точки зрения практики, наверное, это и хорошо, но с точки зрения теории хотелось бы побольше математики увидеть. Вот здесь мы математику увидим. Поэтому будут формулы, поэтому у меня нет слайдов. Я буду в режиме как-то лектору доски, да? Но я только на планшете буду писать. Соответственно, давайте мы с вами план сегодняшнего туториала. Значит, сначала мы поговорим кратко про вариационные автокодировщики, которые явились отправной точкой для, собственно, изобретения диффузионных моделей. Дальше мы поговорим про диффузионные модели как частный случай вариационного автокодировщика и посмотрим, как с помощью перехода к диффузионным моделям нам удается избавиться от некоторых недостатков, которые были присущи, таких родовых травм вариационных автокодировщиков. Значит, дальше мы поговорим про стохастические дифференциальные уравнения, потому что диффузионные модели могут быть довольно элегантно сформулированы на языке стохастических дифференциальных уравнений. В частности, выведем с вами динамику Ланжевена и уравнение Фоккера-Планка, то, что нам пригодится. Наконец, мы сформулируем диффузионные модели через score matching. Так, значит, чтобы не забыть. И, значит, последнее, мы поговорим про так называемый classifier guidance, как способ построения условно-генеративных моделей на основе, значит, обученных в безусловном режиме диффузионок. Значит, это вот наш план. Что хотелось бы мне в ходе туториала донести, то, что диффузионные модели, они допускают взгляд с разных сторон на себя. То есть на диффузионные модели можно смотреть вот как на некую хитрую модификацию вариационного автокодировщика, и этот взгляд одну интуицию дает. Можно смотреть на диффузионные модели как на модель, которая решает задачу скор-матчинга, это дает немножко другую интуицию. Можно смотреть на диффузионные модели как на дискретизацию стохастического дифференциального уравнения. Это дает некий третий взгляд. Каждый из этих взглядов обогащает функционал диффузионных моделей. И в этом смысле каждый из них полезен, и поэтому хочется с разных сторон на один и тот же процесс посмотреть. Итак, значит, давайте мы начнем с вариационного автокодировщика. То есть что это такое? Это нейросетевая модель... Да. Are there any English-speaking participants? Okay, then I'll switch to English. So we'll start from a variational autoencoder. This is a deep latent variable model that allows us to build low-dimensional nonlinear manifolds of high-dimensional data. So we assume that we have data X. This is our sample. So it consists of n objects, and each object lives in a high-dimensional space and might have a very complicated structure. And we assume that although the real data lives in high-dimensional space, actually it forms a low-dimensional nonlinear manifold. And each object has a latent representation, Zi, which lives in a small-dimensional latent space. So this is a pretty standard problem of how to build nonlinear low-dimensional manifolds given a large number of high-dimensional samples. And one approach to this problem is to build a variational autoencoder, which is a generalization of well-known autoencoder model, which is known from 90s. But this is a pretty nice generalization, which allows us not only to build a model which allows us to construct low-dimensional manifolds, but it is also a generative model. So it allows us to generate new objects in high-dimensional space with dimension d large. So we have a training sample x, x1, xn, and we would like to optimize the likelihood of the training sample. So we somehow parameterize the model with parameters theta, and we would like to optimize this likelihood. The problem is that the likelihood, okay, and we also have a generative model, which looks like this. So this is the model establishes joint distribution over high-dimensional data and its low-dimensional representations. So according to product rule, we may decompose it as follows. Actually, P of z should depend on theta in general case, but this is us who established the model, so we establish it in such a way that P of z is given, so it doesn't depend on any parameters. So the first multiplier is just normal distribution over x, given some nonlinear function, which takes z as an input, and which is parameterized by parameters theta, and some scalar covariance matrix sigma squared times y. So this is our likelihood function. This is how x is distributed if we know its latent low-dimensional representation z. And as for the prior, for the latents, this is just standard normal distribution in a small dimensional space. So this is it. As for function phi, of course, we take deep neural network. So as a universal nonlinear approximator of arbitrary functions. And now our idea is to find its weights, theta, given training sample, x1, xn. So ideally, we would like to maximize this expression with respect to theta. The problem is that P of x given theta is intractable because P of x given theta, this is just marginalization with respect to all latent variables. And since the dependence between x and z is highly nonlinear, it's given by neural network, this integral is intractable. So we can't directly optimize the likelihood of the observed data of the training set. Instead, we can switch to so-called variational lower bound. So we may lower bound P of x given theta by L of q theta. This is lower bound, and it looks as follows. So this is q of z given x phi. So phi are just some parameters which parameterize the exact form of q distribution. Log of joint P of xz given theta over q of z given x phi dz. So this is variational lower bound. So it is always less or equal than the left-hand part expression. And we try to maximize it first with respect to phi, to theta, and second with respect to phi. Since the inequality holds true for any values of phi, if we maximize the right-hand part expression with respect to phi, we make our lower bound tighter and tighter, closer and closer to the real expression which we would like to maximize with respect to theta, closer and closer to the log likelihood of the training sample. So this is the idea. It's known as variational inference. And our Q distribution is ELSER. We may parameterize it as a deep neural network. So this is how variational autoencoders are trained. So please pay attention that we have two groups of tunable parameters, theta and phi, and we maximize the same expression, variation over bound, which is also known as ELBO, or evidence over bound. So we have the same expression, and we maximize the same expression with respect to both theta and phi. So this is in contrast to, say, generative adversarial networks, which are known to maximize different criterions, different objectives with respect to different parameters. And this is why generative adversarial networks are less robust, and it's more problematic to train them than variational autoencoders, because we have different groups of parameters which try to optimize different criterions, and each criterion depends on all parameters. So this is a kind of min-max problem when some parameters try to maximize expression, some parameters try to minimize expression. So here we don't have this problem. Both groups of parameters are trying to maximize the same expression. And this is why training variational autoencoders is very robust, and usually you have no problems with training this model. So now let us have a closer look to ELBO, and let us try to interpret it. So this is expectation with respect to Q of z given x phi. And now I will decompose the numerator. So as a P of x given z theta times P of z over Q of z given x phi dz. And now I will split the logarithm into two parts. So the first part is just the first multiplier from the numerator. So this is expectation with respect to Q distribution of P of x given z theta dz. Minus the second integral. This is expectation with respect to Q distribution of what? Log. Since I put minus here, so I may change numerator and denominator. And this is a log of Q of z given x phi over P of x dz. So what can we say about the second term? Who knows? What is that? Yeah, exactly. This is KL divergence between two distributions. So this part is so-called KL divergence between Q of z given x phi and prior over latence P of z. And we know that it is, of course, non-negative. And this KL divergence serves as a kind of a regularizer. So I will say that this is regularizer. At the same time, the first term is sometimes referred to as a reconstruction term. And now let's try to interpret both terms. What do they mean? What do they serve for? So assume the following ideal situation, that we're able to optimize with respect to all possible Q distributions. And how do you think what will happen if we optimize just the first term? So what do we have in the first term? We have our training sample, X objects. For each object, we derive its latent representation Z. So this is Q of Z given X phi. Then we put this latent representation Z into our likelihood function, and try to predict x. So let me even rewrite it in the following form. So here I wrote the general form with respect to all objects in our training set. I'm going to rewrite it as follows. So this is summation with respect to all objects from our training set. So Q of zi given xi phi. So this is the distribution over latent representation of ith object times log of P of xi given zi theta dzi minus summation with respect to all objects KL divergence between Q of zi given xi phi and P of zi. So this is it, and we try to maximize it with respect to phi and theta. So since both Q and P are modeled by neural networks, so what is that? We have a so-called inference network, which is parameterized by phi. So it takes x as input, and it outputs Q of z given x phi. And we also have a second network, which takes z as an input and outputs P of x given z theta. So it's parameterized by theta. So the first network is known as encoder. The second network is known as decoder. So this is how variational encoder works. So and now let us consider what the first term does. So again, it takes each object of our training sample, so xi. We propagate the signal through encoder, and we output the distribution over zi. Then we take each zi from this distribution into decoder and try to reconstruct xi. So we would like the probability of xi to be as large as possible. So now the question, how do you think what will happen if we skip the second term? So if we optimize just the first term? So it's not too difficult to show and to understand that in this case, if we optimize Q with respect to all possible distributions, we'll end up with the delta functions. So for each xi, we'll have exactly one latent representation zi. So our Q distribution will collapse. Because if it does not, then we have expectation with respect to Q distribution, and the log likelihood of xi will be lower than if we took just the most, if we took zi with the highest likelihood of xi. So this means that the first term is trying to minimize the reconstruction error. So we take xi as an input of encoder, and we would like to obtain as an output of decoder distribution which is with respect to which the probability of xi is as high as possible. So this is the reconstruction error. And we try to minimize the reconstruction error. And of course, if we try to minimize the reconstruction error, the best way to do it is to simply learn point representation for the in the latent space. So for each object xi, there should be exactly one point zi. So this is what the first term does. And what does the second term? The second term says that our Q distribution in the latent space for each object should be more or less similar to the prior distribution. So if it deviates too much from the prior distribution, the second term will be very large, and since it's negated, so the whole expression will be very small. So we'll penalize large deviations of our Q distribution from our prior distribution. And that's quite important, because this is exactly what allows us to use variational autoencoder in generative regime. So let us try to visualize it somehow. So suppose that this is this space, say it's two-dimensional. So we have prior distribution, which is standard normal distribution. So this is its level set. So this is prior distribution for all zi's. And we learn some Q distributions, some conditional distributions for zi given xi. So this is a latent representation of the ith object. And we learn some kinds of such distributions. Traditionally, people use fully factorized Gaussians for Q distributions. So we can't learn, say, delta function, because KL divergence between delta function and our prior will be too large. So this is not the case. We also can't learn some such distribution, because it's too far from zero, from the origin. So it's too far from, again, from prior. So again, the penalty will be too high. So what we actually learn is some blue distributions which lie pretty close to the prior distribution. This happens because of the second term, which penalizes large deviations in terms of KL divergence. And KL divergence, we know that this is a kind of a similarity measure between two distributions. So we try to keep our Q distributions. So this is it, Q of Zi given Xi phi. We are trying to keep it as close to the prior distribution as possible. Of course, if there were not the first term, then all our Q distributions simply coincided with the prior distribution, because the KL divergence would be zero in this case. But if all our Q distributions are the same, then of course the reconstruction term will be pretty high, because our model is no longer able to distinguish between different Xi's. So for all Xi's, we have exactly the same latent representation. This is pretty bad, and the first term prevents from doing this. So the optimization of both terms is a kind of compromise, which yields us exactly what I plotted here. So we have Q distributions which are similar to our prior, but they're not the same. And so this is how a variational autoencoder trains. And now what we are able to do. Of course, we may apply this straightforwardly, and for all objects from our training set, for all Xi's, we may obtain the distribution of its latent representations. So Q of Zi given Xi. But of course, this is not the main functionality of variational autoencoders. So variational autoencoder is generative model, and the main goal of variational autoencoder is to generate new X's. So how can we do this? So this is our model, two networks. After we have trained them, we now may run variational autoencoder in generative mode. So what do? We generate Z from prior distribution, and then we generate X, that is Z hat, from P of X given Z hat and trained values of theta. So this is generative mode. In generative mode, our decoder takes Z's from prior distribution. And please keep attention, this is the crucial point. During training, variational autoencoder always took Z's from Q distribution. So our decoder always took Z from Q distribution, because we have a Q here, we have a Q here. So the expectation is always taken with respect to Zi from Q distribution. And in generative mode, we take Z from prior distribution, from P of Z. Of course, we already understand that, well, they're more or less similar. So ideally, what we would like to have is to have a prior distribution as simply direct mixture of our Q's. So it would take the latent representations of all objects from our training set. If we add them together, if we mix those distributions, ideally we would like to have prior distribution. If this is the case, then everything is okay. But of course, in real life, the situation is a bit different. So we do not have this equation. So only some approximate relation. And this tends to very bad effects and variational autoencoders. When in training mode, everything is okay, so the reconstruction error is pretty small, we're able to generate good reconstructions of our objects from our training data. And our decoder always sees Z's from Q distributions. And when we start running variational autoencoder in generative mode, instead of Z's from Q, we take Z's from prior distribution, from P of Z. And since these distributions are different, Especially this is the case in multi-dimensional spaces. So in two-dimensional space, maybe it's not so clear because I can, well, cover my red distribution with the numerous blue distributions. But if this is high-dimensional space, in practice, it's not able, it's not possible to cover the whole red distribution. And as a consequence, we have the following situation. In generative mode, our decoder takes Z, which it never saw during training. And of course, if it never saw during training, well, it generates something. But the distribution in X space is not too realistic. And this is what we observe in practice. So when we train variational autoencoders, for example, on a set of images, we have very good reconstructions. So if we take image from training data, if we propagate it through encoder, then generate the corresponding Z from Q distribution and propagate it through decoder, we'll obtain a pretty good reconstruction of the image from training data. But if we run variational autoencoder in generative mode, well, it generates some images, but they're quite blurry. So they're not too realistic. This is probably the main disadvantage of variational autoencoder. For example, in comparison to generative adversarial networks, we know that GANs generate much more realistically looking objects. Of course, GANs have its own problems, but this is probably the main motivation for diffusion models. So now I understand that the problem with variational autoencoder is that it can't, the latent representations of objects from training data can't cover the whole prior distribution. And now let us think how we can overcome it. And some concluding remarks. Initially, variational autoencoders was the way for finding lower dimensional manifolds of high dimensional data. And only very recently it appears that actually variational autoencoders can be used in alternative way, not as a way for finding lower dimensional manifolds, but to the contrary, as a way of finding high dimensional representations of X data. For example, such models as hierarchical variational autoencoders, such models as VQ variational autoencoder, vector quantization variational autoencoders, where the latent representation has even a larger dimension than the X itself. So this is the case when D small is larger than D large. And in these cases, it appears that in many cases, such overparameterized variational encoders are able to produce very realistically looking objects. And again, this was another motivation for the diffusion models. So now let us switch to diffusion models. So I think, again, everybody knows that the idea of diffusion models is following. We take object from our training data, so we call it X0, and then we start to noisify it by reducing the useful signal and by injecting some Gaussian noise. And we build a chain of intermediate representations until we reach some T large. So at each step, what do we do? Xt plus 1 equals square root of 1 minus beta xt plus square root of beta times epsilon, where beta is some small value, which is much less than 1, but it's positive, of course, and epsilon is just a sample from standard normal distribution. So this is the way how each next object is generated given the previous one. So of course, this means that we may write down q of x t plus 1 given xt in closed form. Also, we may write down how xt depends on x0. So this is square root of alpha t times x0 plus square root of 1 minus alpha t times epsilon, where alpha t is 1 minus beta to the t power. So again, this is pretty straightforward to show. So we just add by induction, for example. So what happens? At each moment, we multiply our signal by a constant which is less than 1, and inject some Gaussian noise. If our variance of x0 was 1, and we may always renormalize, of course, the training set in such a way that it has zero mean and unit variance, then it's easy to show that for rho t, the variance of xt will be also 1. So this is called variance-preserving diffusion. There are also some other diffusion models, but they're all, it can be shown that they're all equivalent, so we'll consider in this lecture variance-preserving diffusion, when we multiply something by a constant less than 1 and add some additional noise in such a way that the total variance is still kept. So this is how it's done, and we also request that alpha t large is much smaller than 1, so it's approximately 0. And this means that q of xt given x0 actually is almost just standard normal distribution. Because from here, we may derive that q of xt given x0 is normal distribution over xt with the mean squared root of alpha t times x0 and variance 1 minus alpha t. So if alpha t is approximately 0, this means that so this distribution, if t tends to t large, so it converges to just standard normal distribution. And this is pretty nice, because you see, any object from the training set diffuses exactly to the same distribution, to the standard normal distribution. This means that if we somehow manage to train this model, and if we run it in generative mode, we take sample from standard normal distribution, we reverse the process, so we go back in time, and we end up with some realistically looking object, because during training, our model will see exactly the axis, well, exactly x t large from the standard normal distribution. So we have no longer mismatch between the latent representations of our training objects and the prior distribution from which we try to generate new objects. Those distributions at moment t large, they're exactly, well, almost exactly the same. So by definition, by construction of our diffusion model. So this means that by construction, again, diffusion model doesn't have this drawback which we mentioned when we spoke about variational autoencoders. Another question, well, okay, formally we can define the model this way. Another question, how we'll train it. And to do this, we note that x0 is observed variable. So this is one of the objects from our training data. And all these are hidden or latent variables. And we already know how to train a latent variable model. So we simply need to switch to variational lower bound. So we take log of p of x0. Well, let me remind it in a general case. So if we have a latent variable model, so I will denote it in such a way. So ops means observed variables, hid means hidden variables. So this is a latent variable model. We observe just the first group of variables, and the second group of variables are latent, so they're unknown for us. And if we would like to train the model, given only observed data, so we may always say that the likelihood of observed data the log likelihood of observed data, can be lower bounded by variation of lower bound, that is distribution over all hidden variables given observed variables, and parameterized with some parameters phi, which are variational parameters with respect to which we may make our lower bound tighter and tighter, times log of joint distribution, observed and hidden, given theta, over Q of hidden, given observed phi. So we integrate it with respect to all hidden variables, and we try to maximize this expression with respect to theta and phi. So this is the general scheme, which is applicable for any latent variable model. So let's try to apply it for our diffusion model. So x0 are observed variables, so these are objects from our training data. So here for simplicity, I assume that we have just one object, x0, but of course, in general case, we have just summation with respect to all objects from our training data. And x1, xt are latent variables, so they're not observed. And then we may write down variational lower bound P of x0 given theta, and we may lower bound it by Q of x1, xt large, given x0. Well, actually, I should put phi here, but for diffusion model, the process of how we generate latent variables from the observed ones is fixed. So this is we do it exactly by this equation. So our Q distribution is fixed, and that's why I remove dependence on phi here. So we have a exactly given distribution times log. So in the numerator we have a joint distribution over x0, x1, and so on xt, parameterized by theta. This is our generative model. Divided by q over x1, xt large, given x0, and we integrate it with respect to x1, xt. Okay, now let's try to simplify this expression. So we apply product rule, and we say that joint can be represented as follows. So this is P of x0 given x1, and theta, of course. Theta, yep. So P of x1 given x2, phi, and so on. P of x t minus 1 given xt, theta, and P of xt. And P of xt, this is our prior distribution, so it does not depend on theta. We fix it to the standard normal distribution. Why can we write it down? Because we assume that, again, in generative mode, we'll generate objects as following. So we'll start from xt, and then we go to xt minus 1, and so on to x1, and then we'll generate x0 from x1. So we have a kind of Markov chain. So we diffuse the objects from x0 to x1, x2, and 3, and so on, using Markov chain because of these equation. And we generate objects sequentially in the same manner, but in reverse order. So from xt large to x0. This is why we can write the joint distribution in the following form. So the same for q x1 xt given x0. So this is q over x1 given x0, q over x2 given x1, and so on until we get q over xt large given xt large minus 1. So this is it. And so then we may simplify our variational lower bound as follows. So let us first take the reconstruction term. So this is q of x1 xt given x0 times log p over x0 times x1, and they are integrated with respect to x1 xt. So this is our reconstruction. And then the second term, again, expectation with respect to all q's. And in the numerator, we have x1 xt given theta. In the numerator, we have q of x1 xt given x0. And now let's think how we can simplify this expression. So what can you say about the first term? Can we make it in a bit simpler? So now it's a highly dimensional integral with respect to x1, x2, and so on, xt. But actually, this function depends only on x0 and x1, right? It doesn't depend on x2 and so on. And we know that we may decompose our Q distribution in the following way. And so this means that actually we may simplify the first term as follows. So we only take Q of x1 given x0. So we can compute it in closed form by definition. Log of P of x0 times x1 and theta here, of course, dx1. So good. So this is much more simpler expression because the first term doesn't depend on any other axis, and we have an integral over density that is equals to 1. What can we say about the second term? So actually, formally speaking, this is a negative KL divergence. So this is minus KL between Q over x1 and so on xt given x0 and P over x1 xt given theta. So this is KL divergence, but this is KL divergence in a hugely dimensional space. So this is not too good. So we would like to simplify it. And to do this, let us decompose it in the following way. So here the density stays the same. Here we take log, and we use product rule for the numerator. So we have P of xt times P of xt minus 1 given xt theta, and so on, times P of x1 given x2 theta. And as for denominator, we'll take the following decomposition. We'll take Q of xt given x0. We'll take Q of xt minus 1 given xt x0, and so on, until we have a Q of x1 given x2 x0. So we integrate it with respect to x1 xt. So this is Weyl decomposition. So if we multiply them all, we'll obtain exactly Q of x1 and so on xt given x0. So this is what we can do. Why we use this kind of decomposition? Because now we can group densities as follows, and we'll obtain sum of small dimensional KL divergences. So then I continue. So the first term stays the same. So this is Q of x1 given x0 times log of P of x0 given x1 theta dx1. And as for the second term, I put minus here in order to reverse numerator and denominator. And I take summation with respect to t from 2 to t large. And this will be integral q over xt given x0 of KL divergence between q of xt minus 1 given xt x0 and p of xt minus 1 given xt theta. So this is it, and the last term is just KL divergence between q of x t large given x0 and p of xt large. So this is the simplified form of our variation over bound. And we would like to maximize it with respect to theta. We don't have variational parameters which define Q distribution because Q distribution is fixed. Q distribution defines the diffusion process. So this is simply multiplication of a useful signal by constant less than 1 and injection of some Gaussian noise in such a way in order to keep the total variance to 1. Okay. So now, what can you say about the last term? So this is KL divergence between latent representation of some object from our training data and prior distribution. But by definition, the diffusion process, it diffuses any object from our training data set in the same standard Gaussian distribution at the moment of T large. This was, well, the definition of our diffusion model. And this means that this KL divergence is 0. So there's no mismatch between our Q distributions and between our prior distribution. This is very, very nice. And this is one of the secrets of why diffusion models work so well. In generation mode, they see exactly the same input data as in training mode. Now the first term. The first term usually defines well, just dequantization error, and actually we may just fix this distribution as a Gaussian with some small variance. So the Gaussian on over x0 with the expectation x1 times some small variance. So this may be kept constant. Actually, it doesn't really matter because anyway, the first term is outweighed by the summation by the large second term, which consists of T large minus 1 items. So this is why we may neglect the first term. And so what is remained is just a sum of a large number of KL divergences. So let me say that our variation over bound, which doesn't depend on Q anymore because Q is fixed, is just minus sum over expectation over xt of KL divergences between Q of xt minus 1 given xt x0 and P of xt minus 1 given xt theta. So this is what we actually optimize. This is very good because in order to obtain stochastic gradient with respect to theta, we do not need to run the whole chain from 0 to T large. We may take just arbitrary moment of time, some tau, and consider just one item from this expression, and we'll obtain a stochastic gradient. This is why the process of training a diffusion model is highly efficient. So we do not need to run the whole chain. Because running the whole chain, so the typical number of T large, the typical value is about 1,000. So it's very expensive. But during training, we do not really need it. We just take arbitrary item for arbitrary object from our training data. Okay, now the question, can we compute this term and this term? So let us consider the first item, the first term in KL divergence. So this is it, and here we'll apply our favorite Bayes theorem. So this is Q of t given xt minus 1 x0 times Q of t minus 1 x0 over Q of t given x0. So this is it. And since we have Markov chain, and our xc depends only on the previous xt minus 1, we may neglect this dependence. So we may say that this is simply Q of xt given x t minus 1 times Q of xt minus 1 given x0 over Q of xt given x0. And what is nice here is that everything is computable. So we know how to compute the first multiplier, xt given xt minus 1, by definition of our diffusion model. We know how to compute xt minus 1 given x0, and we know how to compute xt given x0. Because remember, we defined our diffusion model in the following way. So we know how to compute this for any t, and we know how to compute this. So these are just Gaussian distributions. So our xt given x0, here's the equation, and for xt plus 1 given xt, this is just a normal distribution over xt plus 1, square root of 1 minus beta xt, and variance beta e. So we know how to compute everything, and this means that we may estimate this distribution in a closed form. And really, this is just product of Gaussians divided by Gaussian. So the resulting answer will be, of course, Gaussian, xt minus 1, with some mu, which depends on x0 xt, and some variance beta t tilde. So the exact expressions. Well, let us first let us see what is the physical sense of this distribution. So we know that we have some diffusion process which starts from moment 0. So for example, we were somewhere here. So this was x0, and we somehow moved on some random trajectory. And at moment t, we had xt. So we know the ends of our random trajectory. We started from x0, we ended with xt. And now the question, so this distribution, shows how xt minus 1 is distributed if we know that we started from x0 and we ended with xt. So we have some intermediate moment xt minus 1, and we would like to see how xt minus 1 is distributed. So of course, here we could move by another trajectory, but its ending points are the same. So how do you think? What would be the expectation of this conditional distribution? So mu of x0 xt. Any ideas? Well, not the half, because it depends on how large is t. If t equals to 2, and we would like to estimate x1 given x0 and x2, then it might be something about 1/2, something of half of some x0 and x2. But in general case, the intuition tells us that there should be a kind of a linear combination, a kind of weighted summation between x2 and x0. So the expectation should be somewhere in between x0 and x2, right? Does it sound reasonable? And of course, we may write down the closed form expression. So let me just rewrite from my lecture note. So this is square root of alpha t times beta over 1 minus alpha t x0 plus square root of 1 minus beta times 1 minus alpha t minus 1 over 1 minus alpha t xt. Actually, the exact expression doesn't really matter. Just believe that it can be computed in a closed form. And this is exactly this closed form. What is important for us is that this is really a linear combination of x0 and xt. So this is, we may well say that it probably should be somewhere here. So this is the expectation, and there should be some variance. So this is q of xt minus 1 given xt x0. And the variance is given by beta t tilde 1 minus alpha t minus 1 or 1 minus alpha t times beta. Again, the exact expression doesn't really matter. So you may always look in the corresponding papers, or you may derive it yourself. It's not difficult. Okay, so this is the first term in our KL divergence. So this is it. And what can we say about the second term? So this is actually our probabilistic model. This is something we should define ourselves. We should define it up to some tunable parameters, theta. And of course, it's highly desirable to define it in a such way that this KL divergence could be computed analytically, because then it's very easy to differentiate it and to obtain stochastic gradients. So again, we know how to compute this for any value of t. And we need to define xt minus 1 given xt and some parameters theta. And the brilliant idea is to say, well, let us define it in order to be as close to q as possible. So I will define it as qt minus 1 given xt. And well, if I knew x0, I would put here x0 as well. But this is our generative model. So when I generate objects, I do not know x0. But I may predict it using what I know, and I know xt. So I will put here my prediction of x0 given xt and moment of time t. And how to predict it? Well, for example, using neural network. Just what we usually do when we have some difficult problem and we have lots of data in order to tune the parameters. So this is it. So again, this is what is actually trained in diffusion model. So this is deep neural network, which takes xt as an input, which also takes moment of time, t, because in different moments of time, neural network may give different predictions even given the same data xt. And it tries to predict x0. And after it predicted x0, we put this prediction in our Q distribution and obtain P distribution. So P distribution obtained from Q distribution by substituting the real x0 by its prediction given by our neural network. So this is how we defined our probabilistic model. And now let us see what happens to our criterion. So our criterion is here. So this is it. Let's consider just one item here for one moment of t. And so if we consider KL divergence between xt, q of xt minus 1 given xt x0 and p of xt minus 1 given xt x0, so this is KL divergence between two Gaussians, because both distributions are Gaussian distributions. They have the same variance, and what is the only thing which is different is mean of those Gaussians. And so then KL divergence, not surprisingly, that it equals up to some constant, the squared norm of difference of x0 and x theta given xt t. So this is it. And this is exactly the criterion we should optimize when we train our diffusion model. How the training procedure then looks like. So first, take arbitrary x0 from training set. Then take arbitrary tau from 2 to t large. Third step. Generate x tau from x0. We know how to do it because we can compute q of x tau given x0 for arbitrary tau. So this is, formally speaking, this is square root of alpha tau times x0, which I took on the first step, plus square root of 1 minus alpha tau times epsilon. And epsilon is just sample from standard normal distribution. So we generated x tau, and then we differentiate the corresponding item, the corresponding KL divergence from our criterion. So differentiate KL between q of x tau minus 1 given x tau x0 and p of x tau minus 1 given x tau theta differentiated with respect to theta. And this KL divergence up to some constant equals squared norm of difference x0 minus x theta given x tau tau. So we establish neural network which takes noisified versions of objects from our training data, x tau, which takes moment of time, the corresponding moment of time as an input, and it tries to predict the denoisified version of the input. So we put x tau as an input, this is noisified version of x0, and we're trying to predict x0. Of course, we can't predict it in an exact manner, so there'll always be some discrepancy between the prediction and the true value, but nevertheless, this is some quantity which we may compute, which we may differentiate, we may obtain stochastic gradients for the weights of our deep neural network, and we may train our deep neural network with respect to these parameters theta. Okay, so before we establish a break, let us formulate the same objective in a bit different notation, which is widely used in practice and in papers as well, in terms of predicting epsilon. So as we said, so this is our training. Okay, now as we said, x tau equals square root of alpha t times x0 plus 1 minus alpha tau epsilon. We may express x0 from here as x tau minus square root of 1 minus alpha tau times epsilon over square root of alpha tau. And then when we say, let us use as a prediction model x theta of x tau tau, let us use the following model. So we take x tau 1 minus square root of 1 minus alpha tau. This is everything here we know. And the only thing which we do not know is epsilon. Epsilon, which was used to noisify the clean object x0. So let us predict the epsilon given x tau, tau, divided by alpha tau. So this is exactly equivalent reformulation of a diffusion model. So instead of predicting x0 given x tau, let's predict the noise epsilon from x tau. So there's of course one-to-one correspondence, but in practice it appears that numerically it's easier for neural network to predict noise epsilon. Because noise epsilon, this is just some sample from standard normal distribution. So it means that the space of outputs is the same for all moments of time. And since we train single neural network, for all moments of time, for all tau, we have single neural network, where tau is just the input parameter. So it's much easier for deep neural network to predict epsilon than to predict x0. And our criterion function, so if we constant x0 minus x theta x tau tau equals to some other constant. I do not put the exact values for constants. You may easily find them in the literature. Epsilon minus epsilon theta x tau tau. Where, of course, this epsilon here is not just some random sample from normal distribution, but this is exactly that sample of noise which was used to get x tau from x0. So this is an equivalent formulation of a diffusion model. So let us take, say, 15 minutes of break here, and then we'll continue and we'll see how diffusion models can be reformulated on the language of stochastic differential equations. And to do this, we'll need to, I will need to give some brief intro in stochastic differential equations, and this is, well, quite interesting topic. So please do not go far away.